So we're going to look at friction now. And friction is a force between two surfaces. It is basically a force that opposes motion, but in itself can't really produce motion. So basically, when an object is in motion, it can be in contact with another surface, or its surface can be in contact with another surface. This is the type of friction that we're talking about. There are also other forms of friction. It can be going through a viscous medium, which produces what we call drag. But really, we're going to focus on friction between two different surfaces. Now, the contact force between surfaces we know as normal force. Okay? The normal force gets its name from its direction. Normal meaning perpendicular. And it is the contact force that prevents the two objects going together. In addition to this, we also have a frictional force, which is proportional to this normal force, but it depends on how much the two surfaces stick together. Okay? The more the surfaces tend to adhere to one another, the greater the coefficient of friction, and that is going to be very important for calculating friction. Now, the force of friction can be categorized as either being static, if the two surfaces aren't moving with respect to one another. Cases like this could be a stationary object. Could be tires rolling with the road, even though the tires are moving, their surfaces are staying in place with respect to the road itself. And kinetic friction, where if the two surfaces are sliding with respect to one another. Now, generally, our static friction is going to be greater than the kinetic friction, because with static friction, if the two surfaces are stationary, the molecules in each surface are able to make better contact, are able to adhere to one another much better than if they're simply sliding past one another. Again, friction is a force opposed to motion. Okay, so whatever direction the object is going, friction is going to be in the opposite direction. All right, so let's take a look at this little graph here. What's going on right here? Well, we're going to look at the case where the friction is static, first of all. We've got an object on a surface. Here's our surface. Here's our object. We're going to apply a force on this object. And friction is going to push back. Okay. As long as friction is large enough, that box is going to move. Okay? If I put 1 Newton of force to try to push the object, friction will come back with 1 Newton of force. Okay? Not going to move. All right, that's fine. What if I go a little bit more? Let's say I go to 2 Newtons. Okay? Friction will balance that out. Push back with 2 Newtons. 3 Newtons. Friction says, no problem. As much as you go up, I'll keep going up and oppose trying to push on that box as much as I can. Eventually, at 4 Newtons, I will reach the limit for what static friction can do. And this limit is basically mu times n, the coefficient of friction times the normal force. Okay? Once I exceed that, this box is going to start in motion, and friction's still going to be there, but instead of being in the static region where the box isn't moving, I'll be in the kinetic region. Okay. What happens then? Well, now friction just remains at a constant amount. We say that the kinetic friction is equal to the coefficient of friction times the normal force. Whereas before, when we're calculating friction, the static coefficient of friction was less than or equal to mu s times n. Okay? So over here with static, it's ramping up, it's ramping up, it's ramping up. And finally, we reach some value where the object's going to start moving. Okay? So that's very important. All right. We can still have mechanical equilibrium and have kinetic friction. Okay? If I push on that box, and I get that box going, all right, and then reduce the force pushing this forward, I should change that color. I don't want to use the same color. Use blue right here. I have to reduce the amount of force that I have this going forward. Otherwise, if it took 4 newtons to get it going, and this represents like 3.5 newtons, I'll have a net acceleration. Okay? But again, once it's moving, I can lower how much I'm pushing on this box, and it'll keep going regardless of how much force I have. Again, this blue circle represents static equilibrium. It is in motion. It's not static equilibrium, mechanical equilibrium. It's moving, but the net force is 0. Okay. Now let's look at a few different objects. Now before, again, I can find the friction if it's static or it's kinetic by taking the coefficient of friction times the normal force, okay, where this is a material property. Mu depends on what surface is up against another surface, okay? So for instance, steel adheres very well to itself. Not something that you would have thought about, that steel sticks to steel, but actually the metal ions in one surface of steel will stick very well to the metal ions in the other surface. Actually, it's also an interaction of the electrons, but that's a little more complicated. So we see, here's the coefficient of static friction. That's proportionally how much force we have to put on this to get this thing to slide together. And it's about 0.57 for when it's moving. Now, look at these. Here's steel on steel. Here's aluminum on steel. Here's copper on steel. All of these are fairly good numbers. And this is why an aluminum on steel, copper on steel. This is why we want to use some type of lubricant, because without a lubricant, without oil, okay, some type of petroleum lubricant, these things are going to produce a lot of friction and they're going to produce a lot of wear. We're going to wear down the surfaces very quickly. Now, if this were inside an engine with a cylinder and a block, the friction would generate a lot of heat, a tremendous amount of heat. It would cause the metals to expand, and it would actually cause the cylinders to fuse up, okay? Something that we call an engine seizing. Usually when your engine seizes, your engine is damaged beyond repair. It's very easy to destroy an engine, very difficult to repair a seized engine. So what do? Well, we want to make sure that there's oil in the car. Why? Because it decreases the adherence of the metal ions on one surface to the metal ions on the other surface. And with these non-polar lubricants, which oil is a very non-polar molecule, nice long molecule, it reduces the attraction between the two surfaces, and clearly we get a much lower coefficient of friction. Okay. Now, wait until you reach your middle age. Our joints are very well lubricated. We have in them a fluid made out of proteins and water, which is extremely slippery. These proteins are just the right. I think most of the surfaces of it have are very nonpolar, and they allow the cartilage to slide past itself very easily inside the joints with little friction, with little wear and tear. Now, if you injure your joints, the coefficient of friction actually increases within your joints, and that creates what we call arthritis. The two surfaces rub against one another, they irritate one another. Arthro means joint, itis means swelling. The joint swells up, it's very painful. So with regard to injuries, damage to cartilage early in life shows up as arthritis later in life. Wearing out the cartilage, same thing. When that articulated cartilage wears away, you don't have the two smooth surfaces rubbing up against one another, and the synovial fluid becomes less and less. You get arthritis. And sometimes the joints actually have to be replaced due to the high amount of friction between them. So friction is good and friction is bad. Depends on what exactly you're talking about. If you're talking about two surfaces that you want to keep moving with one another, tires on a road, your shoes on the ground, okay? You want the amount of friction to be large so you don't slip. Your tire doesn't slip on the road and your shoes don't slip on the ground. We coat the bottom of shoes with synthetic rubber so they adhere to whatever surface we're walking on very easily. Of course, if we're stepping on ice, well, that reduces the adhesion between our shoes and the surface. And without that traction, it's easier to slip. For surfaces that we do want to slip past one another, we want the coefficient of friction to be low because we want the two surfaces to slide, okay, without much wear and tear. The inside of your joints, the inside of the working parts of an engine, okay? We use lubrication to keep mu as a small number, okay? That's all a lubricant really is. A lubricant is something that is going to reduce the adhesive force, all right? As opposed to getting a large adhesive force for when we want traction. Okay, let's take a look at this. Here we're looking at dragging a block on a surface, okay? What are the different forces that we have? We have the weight of the object pulling down as opposed to the normal force. If this is a level surface, the normal force equals a weight. That's easy. We have an applied force, which is trying to get this thing to move. Now, in this case, I've actually put a spring scale connected to this block, and that allows me to read how much force I have on that block. And as long as the applied force is less than the friction, you know, the maximum static friction, this block isn't going to move. So maybe I'm right here where that star is. My applied force is this much. My frictional force is right there, more than enough to oppose it. That block's not going to move, okay? Whatever I apply, static friction is going to act against that. Now, finally, if I apply enough force that I exceed this value right here, I'm now over here, my applied force is greater than my frictional force, I'm going to have a net force greater than zero, okay? I'm going to have acceleration. My acceleration is going to be greater than zero, and the block is going to start moving, all right? Now, I can actually measure that frictional force, okay? I can determine the frictional force by using the weight of the block and how much force I need to apply to either first getting that block moving, okay? That would be related to the static coefficient of friction, or once it's moving, keep it moving at a constant rate. Okay? So let's say my acceleration is now 0. Now I can say, okay, the sum of the forces is equal to 0 on the block. Weight pulls down, normal force pulls up, friction pulls to the right. The applied force that I'm applying is pulling to the left. This means that my applied force and frictional force are equal and opposite to one another. Okay? Now, if I want to measure the coefficient of static friction, okay, I will put just enough applied force. This is backwards, sorry about that. I'll put just enough applied force on it to get it to move such that my frictional force will just give out before the block moves. Let's say that the, sorry about this, the weight of the block is 58 newtons, okay? That's a typo, that should say 58 newtons. That means my normal force is going to be 58 newtons. That my friction is mu times n, okay? So mu times n is that number right here. My normal force is my weight. And if it took me 11 newtons to get that block first moving, the block weighed 58 newtons, that would be my coefficient of friction for that, okay? Just balancing forces. Let's look at a block on a ramp. We've already seen that if there's no friction, we did this in lab, our acceleration is going to be equal to g times sine theta, where theta represents the angle of inclination here. All right? Now, if I have friction here, okay, if mu is greater than 0, my acceleration should be less than what I get for this case. All right? Why? Because when I got that acceleration, I got that, oops, from this right here. F equals ma. Oops. Let me erase that. That's annoying when it doesn't switch tools. F equals ma. My force, as we see there, is the x component of the gravity, mg times sine theta. Ma is still on the right-hand side. Mass divides out with mass. So A equals g sine theta. Okay? Where you stay at? All right. Now, what's this new force going to do? Once again, I draw a free body diagram. I got that g sine theta by taking the x component of the force. And again, you can see that right here. Fgx is equal to Fg times sine theta. That's mg sine theta. Okay. The y component of the weight is this right here. All right. Resolved all my forces. The first thing I do is I try to find out what the normal force is, because the normal force is no longer equal and opposite to the weight. The normal force is equal and opposite to the y component of the weight, because they're both in the y direction. The weight is no longer the y direction. It's now pointing here. So I've got to take the component that's still in the y direction. So I do the sum of the forces in the y direction. Normal force goes up, weight pulls down. So normal force is equal and opposite to the weight, the y component of the weight. The y component of the weight is mg cosine theta, negative because it's in the opposite direction. And there is my normal force. I need the normal force. Why? Because friction is equal to mu times n. So that's going to go right there. Now, what about the x direction? Before, when friction wasn't present, I just had this term. And that was mg sine theta and I could find A from that. Now I've got this extra term that I just figured out. There's the frictional force with the normal force. We said the normal force is equal to this right here. So now that becomes this. Our equation looks like this, but I can cancel some terms out. This is nice. I can divide both sides by m, so m disappears on both sides. The equation then becomes this, right? Solve for A. Now, this is no different from what we had before, with the exception of we've got an extra term. It used to be A is equal to G sine theta, right? But now we got this extra term, mu cosine theta, and that's a contribution for friction. Got to be really careful here, folks, because friction cannot make something move. So this second term can never be bigger than this first term. If it is, the block's not moving. Because remember, friction can't make things move. It can only slow things down. So this only works for the case where sine theta is bigger than mu cosine theta. Okay? Again, if the second term's bigger, it's just not moving. That's all it means. So that's a block on an inclined plane. Okay. Let's apply this to another condition. Half-Atwood's machine. Okay? Now, here, I've got weight from mass 2 pulling down. I've got tension pulling up. I've got tension pulling this way. But I'm going to add an additional force of friction due to the normal force here caused by the weight here. Okay? How is the system going to move now that I've introduced another force? Do a free body diagram. We did this with the Atwood's machine, so mass 2, which is the suspended mass, is really easy to do. It's moving in the y direction. It has acceleration downward. That's why we have negative m2a. Tension pulls up, weight pulls down. Here's our first equation. Okay? Same thing we did for the Atwood's machine. What about block number 1? Well, it's being pulled by tension this way and the frictional force this way. We have to remember the frictional force is equal to mu n. That's no problem. This is just equal and opposite to this. You know, sometimes I write this as W1. Don't get confused by that. But basically, this is just becomes mu mg. This is m1. Okay? No inclined plane here, so we're good. So you go ahead and calculate the y forces for this case. That's trivial. Again, normal force is just m1g. We knew that. We could figure that out. Do it for the x case. The sum of the forces, tension minus friction, equals m1a. Now we're going to solve in for friction. It's mu n. We know that n is m1g, so we substitute that in. Now we have an expression for mass number 1. Okay. Here's my equation from mass 2. I did that first. Here's my equation for mass 1. All right. I will substitute one equation into the other. I will plug them. No, I'll just set them equal to one another. Tension equals tension. Set them equal to one another. That gives me an equation, which I can just solve for acceleration. Put all the g terms on this side, put all the a terms on this side, just like we did with Atwood's machine. Now solve for a. We group like terms together. Divide both sides by m1 plus m2. And this looks very much like the Atwood's machine. Okay? Few differences. All right? With the Atwood's machine, it was minus, whoops, clear. It was minus M1 over here, but instead it's minus mu M1. Okay, very, very similar. But again, you still have M1 plus M2 in the denominator, you still have G over here, you still have M2 over here. So the half Atwood's machine with friction is just a little more complicated than the Atwood's machine, but really not that bad. What about a block on a ramp? Oh, this is the inclined plane problem. Oh, let me clear that. So we got to consider this angle of the block. We've got a normal force here. We got a tension here. We've got the weight pulling down here. So you got this component of the weight. We have friction going here. We got tension going here. We got weight going here. Okay, so we got to figure out all those different forces. This time, we have the inclined plane instead of a flat plane. So that changes friction just a little bit because it changes the normal force a little bit. M2 is no different. We still get the same equation we've gotten from Atwood's machine, half Atwood's machine. That's the same. Nothing changes. But for a block on the inclined plane, we've got to resolve the force due to gravity, or weight. Here's the y component. Here's the x component. Okay. It is the y component that is used to find the normal force in the y direction. So again, looking at the normal force, now instead of the normal force being m1g, it's m1 cosine theta, because it's equal and opposite to the y component of the weight. Okay. Why do we need this? Because we're going to plug this into our friction equation. Right? We need that to put into right there. Okay. All right. Now we do our x equation. This is the important part. We have the tension pulling it uphill. It's in the positive x direction. We have the x component of the weight pulling in the negative direction. We have the friction opposing motion. So this force plus this force plus this force is equal to m1a. All right. I will plug this in here. Okay. This is this. Clean it up just a little bit. And this is our equation. Tension, x component of the weight, friction, add them all up, equals ma. So my final equation becomes this. Now that's just putting t on the left side and putting everything else on the right side. I need to combine that with my equation I got from mass 1. I'm sorry, mass 2. Here's that equation. Here's the equation I just came into. So I combine these two equations. Okay. The rest is algebra. Just got to take a lot of steps here. And I get all my A terms on one side, all my non-A terms on the other side. In my final equation, it looks complicated. It's not as bad as we think if we break it down. What do we see? We still see m1 plus m2 in the denominator. We still have m2 right here. Friction's a little different. Okay. Instead of friction simply being mu times m1g, it becomes mu m1g times cosine theta. And then finally, because it's an inclined plane, we also have some contribution from gravity, which is also slowing it down. If you plug in numbers, here is a 0.1 coefficient of friction that's very, very low. 37-degree angle. M1 is 7 kilograms. 7 kilograms. M2 is 12 kilograms. It accelerates at a rate of 3.7 meters per second squared. Oh my, 3 blocks. Well, quite honestly, you can put as many blocks together as you want, okay? Just gonna get more equations. Be careful though. It's not just tension we don't know. It's actually 2 tensions we don't know. We don't know T1, we don't know T2, and T3. T1 cannot equal T3. Otherwise, this block would have no net force on it. It wouldn't accelerate. So basically, we don't know the acceleration. That's an unknown. We don't know T1, the tension between M1 and M2, and we don't know T3, the tension between M2 and M3. Okay, 3 unknowns. We're going to get 3 equations, 1 for each block. Okay, this block and this block are easy. M1 and M3 are just like the M2 that we had, the Atwood's machine, the half Atwood's machine, the inclined plane pulley system. Right? So we do them just the same. All right, here's our first equation. T1 equals M1G minus A. Here we're actually putting numbers. Here's a second one. T3 equals M3 A plus G. Okay, 1 block's going up, T3 is going up, M3 is going up, M1's going down. And now you just need to do the middle block. And the middle block's a little tougher because you have T1 pulling it to the left, T3 pulling it to the right. It's moving to the left, negative acceleration in the negative x direction. So the friction will be pulling in the opposite direction that it's moving. Put it into an equation. Okay. Well, normal force is just showing that the normal force is equal to the weight because it's on a level ground. But here's my forces in the x direction. T1, T3, and the frictional force, which is 3.4 newtons. So for the sum of the forces on M2, T3 pulls to the right, T1 pulls to the left. The frictional force is also pulling in the x direction. I add them all up. They're equal to M2A. Got to be a little careful here. T3 is pulling in the positive direction. F would actually be pulling in the positive direction too. So that's why you have these 2 negative signs right there. So really, if I weren't so careless, yeah, T3 is positive, F is positive too. I get this relationship right here for acceleration. And now all I need to do is plug in my T1 and T3 equations from M1 and M3 in there. And there that is, okay? Not so transparent. There's the one tension, there's the other tension, and there's a friction. And we find out that it's accelerating at 2.3 meters per second squared. Okay? But 3 unknowns, 3 equations. We can also solve for the tensions in the end. Plug in my acceleration in my T1 and my T3 equations, and I can find those unknown tensions. All right. There are other types of friction. As we said before, we can also have drag, okay? Drag is due to any viscous medium, can be air, can be water, can be molasses, but we really don't do much of that here.